Good evening everyone, welcome to Gate Academy Global. So our today's topic, as I told you, that is the drawbacks of the delta modulation and also signal to quantization noise ratio in delta modulation. So good evening Pragati, Lakshmi, Renu, Shri Krishna, Animesh, Ajay, Govind. So all of you, good evening. Mayank, thank you. Nazia, good evening. Thank you very much, Nazia. Nitish, good evening. Amit, good evening. So, Nutan, yes, good evening. Welcome all of you. And let's start the today's topic. And the today's topic is, as I told you yesterday, and if you have been watched that video, then you will be knowing what we are going to discuss today. Okay, so let's start with the drawbacks of delta modulation. Drawback of delta modulation. So if suppose this is the message signal amplitude and it is the time axis and it is the message signal amplitude. Suppose the message signal is starting at this point and it is going like this. This is the message signal. Okay, so this is your message signal which is having the slope which is very high and it is having the constant slope at this duration. So in this duration the message signal slope is almost constant. How many hours are remaining in this communication course? Around 10 to 15 hours will be remaining in this particular course. So one class I will take for information theory, 1 or 2 class, and one class I will take for band pass transmission, and I will tell you in the end of the video what is our plan for the next 3 to 4 days. Okay, I will discuss with you all the plan for the next 3 to 4 days. I will try to finish it before Sunday with that much detail which I am providing since last 3 to 4 days. So I will try to maintain that detailed explanation in the upcoming 3 to 4 days, and the plan will be different, and I will tell this what is the plan at the end of the video. Okay. Yes, Neeraj sir is going to start communication as you might have seen in the Gate Academy channel. 5 p.m. there was a live, and that was the announcement for the communication, and that might be going into the Gate Academy main channel, so you can watch that video later. Okay, so he will be teaching you in Hindi, and I am discussing the communication in English. Okay, so he will be dealing with communication in English, in Hindi in the main channel. So my EMT will finish on 9th of October. Yes, Sachin, under 100 rank would be good for the getting into the PSU. Okay, Sachin, if you want to go into the PSU via gate, then the under 100 rank would be enough. Okay, so we are discussing that this is our message signal and it is having the high slope in this duration and it is having the zero slope in this duration. And suppose our quantized signal, which is MQT, okay, so this is MQT, which is the output of the integrator, is starting from the 0. So output of the integrator is starting from 0. So at this point, if you compare, what will be the output of the quantizer? What will be the output of quantizer? Tell me at this point, if I compare, what should I get at the output of the comparator or quantizer? Yes, plus delta. Okay, so if I compare these two, this is the message signal, this is the quantized signal, so we will get the plus delta, and plus delta up to the time duration Ts. Okay, again if I compare, the message signal slope is higher than the quantized signal, the output will be again plus delta. Here also it will be plus delta, here also it will be plus delta, here also it is plus delta. Okay, so in this way we will get the output of the comparator, or you can say the output of the integrator. The output of integrator you will get like this. Now when we compare at this point, it will be minus delta, it will be minus delta, again it will be plus delta, it will be plus delta, minus delta, plus delta, and so on. Is this diagram is clear to everyone? Can anybody tell, is this diagram is clear to everyone? Okay, so I think it is clear to everyone. So the difference between the quantized signal and original message signal is called quantization error. So this is the error, and we want to have our staircase signal to follow the message signal. This is the staircase output which we are getting, and we want to have the staircase output to follow the message signal, because at the receiver output of integrator is nothing but, at the receiver the output of integrator is nothing but your actual message signal, and by passing it through the low pass filter or the reconstruction filter you will recover your message signal. So it is important to staircase signal to follow the message signal. So it is very much important that our staircase signal should follow the message signal. But in this particular case, if you pass the staircase signal which is MQT from the reconstruction filter, what you will get, as I told you, that to know the output of reconstruction filter we have to connect the peak value of the signal. So if we connect the peak value of the signal, staircase signal, what we will get? We will get the signal which is very much different from the message signal. Our original message signal is having the slope which is starting from here, and the output of the reconstruction filter will look like this signal. So this is the original message signal, and this is the actual output at the reconstruction filter. So these two are very much different here, and here also our original message signal is having almost a constant slope, but this is nothing but a hunting around this constant slope. It is oscillating, it is continuously oscillating around this message signal MT. So our message signal should be constant, but here the amplitude is continuously changing. So there are two different types of change, or there are two different types of error we are looking here. First is our message signal is here, and it is our output of the reconstruction filter. Both the signals are different, so we are not getting the actual message signal. Here our message signal is having a constant slope, and the output of the reconstruction filter is oscillating, it is changing the amplitude. So here also we are getting the incorrect output. So we can say that it is going to produce some error, and these error are known as, one is known as slope overload. This error is known as slope overload error. This error is known as slope overload, and this part of the error where the slope is constant is known as granular noise. Granular noise. So slope overload error will occur when the slope of the message changes too fast. So slope error load occurs, it occurs when amplitude of message signal, or in fact the slope of the message signal varies too fast, okay, and granular noise will occur when the slope of the message signal is constant. When the slope of the message signal is constant. Is it clear? Okay, so now we can avoid this slope overload. What would be the condition to follow the message signal? So the condition to follow the message signal is that the slope of this staircase should be equal to the slope of message signal, or it can be greater than the slope of the message signal. So the condition to avoid slope overload, so to avoid slope overload, error, the condition is the slope of staircase should be greater than or equal to slope of message signal, magnitude of slope of message signal. So magnitude of slope of message signal. Okay, so what is the slope of a staircase? Can you tell what should be the slope of the staircase? So this is the height. Okay, so this is the height, which is nothing but a delta. So the step size is delta, and the width, this width is nothing but a TS. You can see that this width is TS. TS to 2TS, 2TS to 3TS, 3TS to 4TS. So the width is TS. So what should be the slope? Shubham, the same communication system which I am telling, he is also telling in the main channel. Both the communication are same. From anywhere you can study that. Delta upon TS. So this is the delta upon TS. The slope will be delta upon TS, and it should be greater than equal to the magnitude of slope of message signal. So it is magnitude of slope of message signal. Okay, so delta by TS should be greater than equal to magnitude of slope of message signal. So this is the condition to avoid the slope overload error. Now, if the message signal is single tone sinusoidal, if message signal MT is single tone sinusoidal, that is AM cos omega MT. If the message signal is single tone sinusoidal AM cos omega MT, then what should be the condition? What should be the condition to avoid the slope overload? So according to this, this is delta into Fs. 1 upon Ts can be written as sampling frequency, and it should be greater than equal to magnitude of slope. So you have to differentiate the message signal, and when we differentiate it, we will get AM into omega m, and that is the magnitude of slope of message signal. And this message signal amplitude, we can say that it is less than equal to delta into Fs divided by omega m. Is it clear? Is it okay? Slope of the message signal is constant, means it is flat, it is having the slope 0. For a constant line, the message signal slope will be 0. Slope of the message signal is constant, it means that the slope is 0. Yes, Rushikesh, that is DPCM and delta modulation are important for instrumentation also. Okay, granular noise is coming because when you will compare the message signal with the quantized signal, there will be the change in the step size. There will be continuously positive and negative going steps, because when you compare at this point, the message signal is less, so the slope, the output of the comparator will be minus delta. So here it is plus delta, now it is minus delta. So because of the plus minus delta you are getting in this part, you will get some error at the output of the reconstruction filter. It is continuously changing. Okay, Akansha, is it clear? Because the steps are changing where the signal is having the constant slope. The steps are changing where the signals are having the constant slope. Okay, and because of the change in steps at the output of reconstruction filter, the amplitude is changing, but actual amplitude of the message signal is flat, it is constant. So up to this point it is clear to everyone the what condition for the message signal amplitude. If the message signal is sinusoidal, the condition to avoid the slope overload, the amplitude of the single tone sinusoidal signal should be less than equal to delta fs upon omega m. It should always be less than this quantity. Now let's calculate signal to quantization noise ratio in delta modulation. Signal to quantization noise ratio in delta modulation. Next heading is signal to quantization noise ratio in delta modulation. Akansha, obviously delta modulation is better in application wise according to application because the bandwidth is less in case of delta modulation. Okay, now as we are having the comparator with us in the delta modulation block, it is the comparator characteristics. Okay, so it is input and it was output. Okay, so in this way we are having the block diagram of communication where block diagram of delta modulation where we had this comparator. So this comparator is having the amplitude minus delta and plus delta. So tell me what will be the output if the input is 0? What will be the output if the input will be 0? If the input is 0, say the input is 0, if the input is 0, you are not sure that what should be the output because the output can be plus delta and the output can be minus delta. It is not, no, you are not getting this point. We are saying that if the input is 0, then what should be the output? This is the input output characteristics of 1-bit quantizer. Okay, so it is input output characteristics of 1-bit quantizer. So if it is the quantizer and we will have some input, and if it is input and we will get some output, and the characteristics of input and output is given, and if input is 0, then somebody can take plus delta and somebody can take minus delta. Yes, Animesh, you are correct. Okay. So what will be the quantization error? So if this is the case, the quantization error will be, the quantization error is given by input minus output, isn't it? Quantization error is given by input minus output. If the input is 0 and somebody can take the output as minus delta, so if he takes minus delta, so plus delta, then the quantization error will be minus delta. Okay, and if somebody take the quantizer output as minus delta, then he will get 0 plus delta, that is plus delta. So what could be the quantization error in case of delta modulation? What could be the quantization error in case of delta modulation? Tell. Animesh, the quantization error will be plus minus delta. Okay, so the quantization error will be ranging from minus delta to plus delta. Quantization error will be ranging from minus delta to plus delta in case of delta modulation. You can check this. Suppose if the input is plus 1, if the input is plus 1, then the output will be plus delta, isn't it? If input is plus 1, then output is plus delta, and say delta is equal to 5. Say delta is equal to 5. So if input is 1, then the output will be plus 5. The error will be 1 minus 5, which is equal to minus 4. And if the input is 0, the output is, if you take 5, then the quantization error will be 0 minus 5, so it is minus 5. So this is the minimum error which you can get. Minimum error means, because we are getting the negative sign, that's why I am calling it as minimum error. So the minimum error which you are getting minus 5 is equivalent to the height of the step size. The height of the step size was delta. So this minus 5 is nothing but a minus delta. So that is why the quantization error, the minimum quantization error you can get is minus delta. Similarly, if you consider here, it is suppose 2, this is minus 2, input is minus 2. So if you take input minus 2, of minus 2, the output will be minus delta. The output is minus delta means minus 5, because we assume that delta is equal to 5, so it is output is equal to minus 5. So the error, quantization error is minus 2, minus of minus 5, you will get minus 2 plus 5, which is equal to 3. But if you take again input equal to 0 and output is equal to minus 5, the quantization error you will get 0, 0 minus 5, and it is plus 5, which is equal to plus delta. Okay. So if you take input other than 0, like minus 2, you will get the quantization error 3. But if you take input 0, you are getting quantization error 5. It means that if you take the input other than 0, quantization error will always be less than delta or greater than minus delta. It means it will lie between minus delta to plus delta. Can we say like this? Tell me whether it is clear or not. Whether it is clear or not, it will always in the range of minus delta to plus delta. It may be equal to minus delta, it may be equal to plus delta. Is it clear, Animesh, now? Yes, okay. So this is the case, and in case of pulse code modulation, tell me, in case of pulse code modulation, what was the quantization error range? Yes, Nutan. In case of pulse code modulation, what was the range of quantization error? What was the range of quantization error in pulse code modulation? Yes, minus delta by 2 to delta by 2. Okay. So the difference is clear. The delta modulation is having the quantization error which is your plus minus delta, and in the pulse code modulation we are having the quantization error which is ranging from minus delta by 2 to delta by 2. So let's derive the signal to quantization noise ratio. Let the signal to be quantized. Signal is mt is equal to am cos omega mt. Okay, let the signal which is to be quantized is am cos omega mt. So what is the highest value of this? So the highest value is am and the lowest value is minus am. So that is okay. And if we are applying the delta modulation, we never want to have the slope overload error. So to avoid slope overload error, okay, so to avoid slope overload error, you know that this am should be less than equal to, okay, so to avoid slope overload error, am should always be less than equal to what? Delta fs upon omega m. So if you want to calculate the signal power, if we want to calculate signal power, so the signal power, say S is equal to how much? We know that it is sinusoidal signal, so the signal power is given by amplitude square divided by 2. So this is the message signal, the signal power is given by amplitude square divided by 2, and to avoid slope overload error, the message signal amplitude should be delta fs upon omega m. So it is delta fs upon omega m whole square divided by 2. So it is equal to delta square fs square and 4 pi fm square into 2. Oh, the camera has been switched off because of the battery. Okay, so is it clear? Is it visible now? Yes. So now I was saying that let the signal is message signal is sinusoidal, single tone sinusoidal. So this is mt is equal to am cos omega mt. The highest value and the lowest value we know. If it is a cosine signal, it is between the plus am and minus am. And to avoid the slope overload error, the amplitude of the message signal in case of single tone sinusoidal should be less than equal to delta fs upon omega m. And if you want to calculate the signal power, because it is a sinusoidal signal, the signal power can be calculated by amplitude square divided by 2. So it is amplitude square divided by 2. The amplitude is given by delta fs upon omega m. So delta fs upon omega m whole square divided by 2. It is delta square fs square omega m. Omega m means 2 pi fm. So 2 pi fm square if you do, so you will get the 4 pi square. Okay, so we will get 4 pi square fm square into 2, or you can say that the signal power is coming as delta square fs square upon 8 pi square and fm square. Okay, so this is the signal power you will get, and this is the signal power. Now the left is quantization noise power. So we know that this quantization error is distributed between minus delta to plus delta. So it is distributed between minus delta to plus delta, like this. It is distributed between minus delta to plus delta. Okay, minus delta to plus delta. So the height will be 1 upon 2 delta, and this is x, because this is q, let us say. This is the quantization error. So the quantization error is ranging from minus delta to plus delta, and here also we are assuming that it is uniformly distributed. Okay, the quantization error is always assumed as uniformly distributed, and if the quantization error is not uniform, it will be given to us. So basically most of the time in the practice also we consider that the quantization noise is uniformly distributed in the given range. If it is pulse code modulation, it will be uniformly distributed between minus delta by 2 to plus delta by 2, and if it is delta modulation, it will be distributed between minus delta to plus delta. So it will start from minus delta to plus delta, and the height will be 1 upon 2 delta. Okay, so what should be the quantization noise power? So tell me what will be the quantization noise power. How will you calculate the quantization noise power? How will you calculate the quantization noise power? Delta square by 4, no. Delta square by 4, no. The lowest value is given by A. Here we are having the lowest value. A is equal to minus delta and B is equal to plus delta, and we know that to calculate the quantization noise power, we will calculate the mean square value of quantization error. So mean square value of quantization error is given by NQ is equal to B square plus AB plus A square divided by 3. Mean square value of quantization noise power is nothing but, quantization noise is nothing but b square plus ab plus a square by 3. So what is the value of b? This is delta square. What is the value of a? Minus delta, value of b plus delta, a square delta square divided by 3. This will get cancelled and you will get the delta square by 3 as quantization noise power. Delta square by 3 you will get. Yes, Rohan, delta square by 3, Shri Krishna, correct. Yes, Nandita, delta square by 3 you will get. So the quantization noise power will be delta square by 3. So we want to calculate the signal to quantization noise ratio in case of delta modulation. So the signal power divided by noise power we want to calculate. So the signal power divided by noise power, signal power divided by noise power. Okay, so what is the signal power? The signal power is delta square fs square upon 8 pi square fm square multiplied with noise power, which is delta square divided by 3. So this delta square and delta square will get cancelled and signal to quantization noise power is 3 upon 8 pi square fs upon fm whole square. This is the case of single tone sinusoidal signal and this is called SQNR. So signal to quantization noise ratio in case of delta modulation will be 3 upon 8 pi square fs upon fm whole square. So is it clear? Is it clear to everyone? Okay, very good. So let's discuss the next topic. So this is all about the delta modulation, and we can avoid the slope overload by adaptive delta modulation, but adaptive delta modulation is not in the syllabus because they have never asked the question from the adaptive delta modulation. It is nothing but a variable step size, the system with a variable step size, because in this type of quantization, in the delta modulation or in pulse code modulation, we keep the step size fixed. So to avoid that slope overload error, we have to follow the step size. We have to follow the slope of the message signal. So for that you have to increase the slope, you have to increase the height of the step size according to the slope of the message signal. As you can see that here the slope is varying very fast and our steps is fixed, so it is varying like this. The height is plus delta, so height is delta, so it is not able to follow the message signal. This staircase will not able to follow this message signal. So what you have to do is, if the slope is varying very fast, then the height of the staircase should also be very fast, like this. So the height of the staircase should vary, and the height of the staircase is nothing but the step size. That means the step size should also change according to the fast varying message signal. So if we consider that, we will be having the system which is known as adaptive delta modulation. So in case of adaptive delta modulation, we vary the step size according to the variation in the message signal. We don't study about the SQNR for the granular noise because the message is barely constant in practice. The amplitude of the message signal most of the time will be varying. So that is why we don't study it for the granular noise. Okay, So now our next topic is time division multiplexing. Our next topic is time division multiplexing. No, Shruti, it is not in our syllabus, and you will not find any question from the adaptive delta modulation in the past 25 years of the GATE question. So that is why we actually don't teach that adaptive delta modulation. It is just a theoretical thing. So it may be asked in your ESE exam, but because this crash course is especially designed for the GATE 21, so we will not study that. Bandwidth, we already know what is the bandwidth of delta modulation. You have to put n equal to 1 because the number of bits required is 1 only. Okay, so in the time division multiplexing, what happens is, suppose we are having the one message signal. This is our message signal, say M1. You know about the multiplexing, right? Multiplexing means many to one. If you are having many users and we want to use a single channel to transmit our data, so there will be a multiplexing should be applied, because the multiplexing is many to one. There will be many users and we will transmit our data using the single channel. So multiplexing means many users. So we will be having many users. Yes, Ritesh, super heterodyne is important, and I have already discussed in the channel, in the main channel it is already there, concept of image frequency. If you will search, you will find the detailed explanation of super heterodyne receiver, and not that much important compared to the other topics. It is less important, and they are not asking questions from the super heterodyne receiver in the past 3 to 4 years, and because they are giving focus or giving weightage to the random variable random process and the noise in digital communication or digital communication. So they are giving less weightage to the analog part, analog communication part, but they are the basics of the communication, because the modulation concept comes from the amplitude modulation and then frequency modulation, angle modulation. That's why the angle modulation and the amplitude modulation both are important topics, but because nowadays we don't use AM receiver, so in the actually super heterodyne was designed for the AM receiver especially, so that is why they don't ask questions from the image frequency concept, but it is moderately important. We cannot say less important, because they have asked the question in the previous year, but the concept of the super heterodyne receiver is around 1.5 hours. So you can spend 1.5 hours to learn the concept, and if the question will come from that topic, you will be able to solve. Signal to quantization noise ratio in DPCM is nothing, it is same as PCM, there is no change. Yes, super heterodyne question from the super heterodyne receiver will always be there in the test series, whether it is from GATE Academy, whether it is from the ESE Academy or from the ESE. There will be some question from the super heterodyne receiver, because the test series is designed to have all the topics in your command. Because if we cover broadly the test series, by the test series you can cover all the topics broadly. So that is why in the test series everybody will keep the question from each and every possible topic. Hello Saurabh. So are you watching this crash course series? Now I am actually discussing each and everything in bit detail, Saurabh, because the digital communication many students face problems. So that is why if you will watch this videos crash course, then you will see that most of the thing I discussed in the pen drive course, I am discussing it here also. So next time when I will teach communication in the pen drive or in the live class, that will be in another level, because that I am giving everything what we teach, what we study in detail in the crash course. So I will change the communication in the next level. Yes, Priyajit, the CRC I will give soon in this month only. The cyclic redundancy check and circular waveguide I will cover in this month only. Okay. One question: it is necessary for electronics students to study the electrostatic or magnetostatic? I will say yes. It is, if you want to have the good command over the subject, so you should not leave the subject. As I always used to tell that electrostatic and magnetostatic are main background or main basic of the overall EMT subject. So you should not leave the magnetostatic and electrostatic. Okay, Saurabh. So suppose as we are discussing the time division multiplexing, suppose this is the message signal MT and we are having another message signal, say M2T, like this, say M2T. This is the second message signal. So in time division multiplexing, actually in the pulse code modulation, what we do, we take the sample of the message signal at every sampling interval. We take the sample of the message signal after TS second. Okay, after TS second, we take the sample of the each message signal according to the sampling interval. Okay, so suppose this is the time axis. Both the message signals are having the same bandwidth. Both the message signals are having the same bandwidth. The message signal M1T is also having the maximum frequency FM, and M2T is also having the maximum frequency FM. Suppose both the message signals are having same frequency. Okay. Now if we want to sample this signal, if we want to sample it, what should be the sampling frequency? The sampling frequency will be 2 FM for both. Fs will be equal to 2 FM if we want to sample. Okay. So suppose I am sampling the first message signal M1T at time t equal to 0. So when I should take the next sample? So tell me when I should take the next sample. If I am taking the sample at t equal to 0 for the first message signal, when I should take the first next sample for the first message signal? TS, yes, TS, after TS second. So let us say that TS second is completing at this point. So after TS second, because if the sampling frequency is Fs, then the interval is Fs, Ts is equal to 1 upon Fs. So the Ts is the sampling interval. It means that we will take the sample of the message signal at every Ts second. So after Ts second you will take the sample. Again after Ts second you will take the sample here 2 Ts, and again you will take the sample 3 Ts. Okay, so in this way we will take the sample at every Ts second. Now in between t equal to 0 and Ts, we are just waiting to collect the next sample. We are not utilizing the time. Suppose I am taking the sample of the message signal at 0 and I am taking the next sample after 125 microsecond. That is the case of speech signal. So 125 microsecond you are not utilizing, you are just waiting to collect the next sample. Is it okay? So if you are waiting to collect the next sample, can we use to sample it another signal? So suppose you sample any other message signal at time t1, at time t1 which is in between 0 to ts, you are taking the samples of second message signal. So when you will collect the next sample of the second message signal, yes, T1 plus TS. Yes, Niranjana, very good. So we will collect the next sample of the second message signal after TS second. So after TS second means T1 plus TS second. After T1 plus TS second, we will collect the sample of the second message signal. So in this way, we will collect the sample of the second message signal at every ts second, but that will be delayed by t1. So t1 plus ts, t1 plus 2 ts and so on. So at every ts second again you are getting the sample, because both the message signals are having the same sampling interval. So that is why you are getting the samples after every ts second for both the message signals. So you are utilizing, yes, Animesh, Nandita, Saurabh, correct. So you are utilizing that time period, that is t equal to 0 to t equal to ts, you are utilizing that time to collect the sample. So now if I draw the sample values here, so at t equal to t0 we are having the first sample. So at t equal to t0, at t equal to 0 we are having the first sample, and at t equal to t1 we are having the second sample. And at this point at ts we are having the next sample which is greater than this. So this is ts and even more greater. So let's take this one. So this is what the samples of the first message signal. So this is the samples of the first message signal, like this. This is the sample of the first message signal, and after t1 second you are having the sample of the second message signal after t1, and here you are having this signal. This is after t1 plus ts, and here you are having the sample, this one and this one. The fourth sample you will get like this. So now it is this is nothing but a first sample of both the signal, first sample of M1 and M2, and this is the second sample of M1 and M2, and it is third sample of M1 and M2, and this is the fourth sample of M1 and M2. Okay, so this is the first sample of M1 and M2. This is M1 and M2. During the TS second, in the interval TS, you are having the two samples. In every TS second, you are having the two samples right now. In the present discussion, we are having the two samples in the TS interval. Is it clear? So if we represent each sample by 2 bits, then if we represent each sample by 2 bits, then in one interval, in one TS interval, that is starting from 0 to TS, we are having how many bits? So this is the sample of the first message signal. So this is the sample of first message signal, that means M1T, and this is the sample of second message signal, means M2T. I said that if we represent each sample by 2 bits, so how many samples we are getting? So we are getting the 2 samples in each TS interval. So this message signal, sample of the message signal M1 is represented by 2 bits, say 0, 1, and the sample of the second message signal is represented by 2 bits, say 1, 1. Okay, so we are assuming, just to explain you, I am assuming that in the TS interval we are having the 2 samples, one sample for the M1T, second sample is for M2T, and each sample is represented by 2 bits. Okay, so number of bits assigned to each sample will always remain same. If you are assigning 8 bits, so it will be 8 bits for the second sample also. So if I am saying that if the first message signal is having the 2 bits, or the sample is represented by 2 bits, then this sample also represented by 2 bits. So these 2 message signals M1 and M2 are having 2 bits in each sample. Now this interval 0 to TS is called frame. This is called a frame. Okay, so one sampling interval is called as frame in case of time division multiplexing. In time division multiplexing, the TS interval is said to be a frame duration. So the one frame consisting 2 samples in the present case, and this frame is having the 4 bits. So if each bit is having bit duration, TB, if each bit is having bit duration TB, then in the TS interval how many TB will come? So in the TS there are 4 bits, so it will be 4 times of TB. Is it okay? In the sampling sampling interval, or in the one frame duration, 4 bits are coming and each bit is having TB duration, so we can write the sampling interval is equal to 4 times of bit duration. Okay, so we can also write it as 2 into 2 into TB. Okay, now in general I can say, that this 2 is representing the number of user, this 2 is representing the number of bits to represent each sample. Can I say like this? Because in the starting we were having only 2 users, that means the 2 message signals M1T and M2T. Now each user is having the 2 bits. The sample of each user is assigned by 2 bits. So we can say that 1, 2 is representing a number of user, another 2 which is coming is nothing but a number of bits to represent each sample. So we can say that this TS is number of user is equal to n, the number of bits is represented by small n and TB, n into TB. So we will write 1 upon TB is equal to n into n divided by TS, or 1 upon bit duration. What we call bit duration? 1 upon bit duration, what is 1 upon bit duration? Bit rate. Okay, yes, so this is the bit rate. So we can write the bit rate RB is equal to n into small n into Fs. 1 upon Ts can be represented as Fs. So this is the bit rate. So in case of time division multiplexing, the bit rate is nothing but n into Fs. N into Fs is the bit rate of the PCM, and in case of time division multiplexing, you have to multiply by the number of user also. Okay, so you have to multiply it by number of user. So bit rate is n times and NFS. The n, capital N, is the number of channels or number of users. Number of channels, sometimes we call number of channels, and you can say number of users. So it is nothing but a bit rate of the PCM. Bit rate of the PCM is given by NFS, and you have to multiply it by the number of users. So this formula is valid only in the case when all the message signals are having equal bandwidth. All the message signals should have the same frequency. It should have the same frequency, then only the bit rate will be n into Fs. Number of channel, number of user means if suppose we want to, if we are having the 10 users, okay Nilanjana, if we are having the 10 users, okay, and if we want to, if we all the 10 users wants to transmit the signal from the channel, so the number of users means the number of message signals or the number of persons, it is like that. Number of samples taken, no, number of samples taken, yes, we can say like that, number of samples taken. So we are in the one interval of TS, in one interval TS, we are, how many samples we are taking? So we are taking the two samples, so we are taking the two samples, so n will be 2. So in one interval TS, how many samples you are taking, that is equal to number of user. The number of user wants to transmit the message signal from the single channel. So it is like that. When you will read the question, you will understand this. Okay, so let's draw the block diagram of TDM. The block diagram of TDM. Suppose we are having n number of user. So we will use the low pass filter at the input side to band limit the signal. To band limit the signal, because when we take the sample, we should have the band limited signal at the input of the sampler. Okay, the sampling theorem says that a signal should be band limited to FM. So what is the meaning of this line? That the message signal should not have the frequency higher than FM. So for that you have to use a low pass filter. The low pass filter will block all the frequency component which is greater than your message signal frequency. So that is why we use low pass filter, which is also known as anti-aliasing filter. Now this is called a commutator. This is called a commutator. So this is called a commutator. So the commutator is nothing but a electronic switch. It is nothing but a electronic switch, okay, and which is used to sample the message signal. So this is the electronic switch. This switch will be rotating, and according to that, in each rotation we will get the samples of the message signal. So suppose it rotates like this, okay, so when it rotates and it will come back to the same position, so it will take the sample of the first message signal, second message signal, and nth message signal. This is nth message signal. Okay, so it is the nth message signal. So there are n number of message signals. Now it will pass through the quantizer. So this is the quantizer, and after encoding the signal, the quantized signal or the digital signal, we will pass it through the channel. So this is the channel, and then we will decode it, and after decoding we will give input to the commutator again. This is known as decommutator. I am writing it here. This is the commutator. At the transmitter side it is known as commutator, and at the receiver side it is called decommutator. And this commutator should be synchronized. Commutator and decommutator should be synchronized to each other. So we are having the reconstruction filter. Here also it is reconstruction filter. And after passing it through the reconstruction filter, we will get our message signal back, that is M1T, M2T and MNT, like this. So this is the block diagram of time division multiplexer. Yes, Sandeep. So from now onwards, the communication subject will be taken by both of us, Neeraj sir and I will take this communication. So now I am also having helping hand with me, that is Neeraj sir. Okay, so Neeraj sir will also be helping me to give the content to all of you for communication. Okay, so these two switches are synchronized. So they are synchronized. So what is the meaning of this synchronization? So when we synchronize this, when this switch will connect to this pole, the commutator is having number of poles. These are known as poles at which the message signals are connected. So in the first pole, this is suppose the first pole, this is the second pole and this is the nth pole. So when the switch will connect to the first pole, we will take the sample of the first message signal, because our message signal will come at this input and the switch is rotating. So when the switch will connect to this pole, we will take the sample of the first message signal and this switch will be rotating towards second message signal. So when it connects to the first pole, you will take the first sample of the message signal and that sample will be quantized, and after encoding we will transmit it to the channel, and after receiving from the channel we will decode it. And when the switch 1 was connected to this particular, when the switch is connected to the first pole, at the same time this switch will also connect to the first pole. So that is the meaning of synchronization. When the switch will be connected to the first pole, it will also connect to the first pole of the decommutator. Then when it connects to the first pole, the first message signal will come here also, and when it will connect to the first pole, you will receive the first sample, and that first sample you will reconstruct and you will get the message signal M1T. Yes, Rohan, there is nothing like a competition, because communication will be taken by both of us. It means that it is now the GATE Academy will provide communication course, communication content from both of us. That means it will be there will be more session on communication, because the communication are very important. So communication is very important for you, and many students face problem with that, and for me also it is not possible to take the more session on the communication. That is why communication and will be taken by both of us, because sometimes I will be busy in taking the live class, so that time YouTube classes will affect. So to compensate that effect, that time might be Neeraj sir will be taking, and if the Neeraj sir will be taking the class in the live or the pen drive or anywhere, so that time I will be taking the communication in the YouTube. So it is just for you guys that now one more faculty is coming in the same for the same subject, and similarly it will happen for the EMT also. Okay, so it will happen in EMT also. Some other faculty will come later on. Right now no one has come, but some faculty will come for EMT also, and he will also be taking EMT along with me. It is like, you know, there is some institute, right, where you find many faculties teaching one subject, so it is becoming like that only. So the block diagram is clear or not? Yes. So it will happen for all the message signals. When the switch will connect to the second pole, it will also connect to the second pole, and the second message signal you will receive. When it will connect to the nth pole, you will get the nth message signal at the receiver. So like that this time division multiplexing works. No, Santosh, cellular communication will not be covered because it is not in the GATE syllabus. Okay, now let's take another case. Suppose how to decide the speed of the commutator. So now we are going to discuss about the speed of commutator. Speed of commutator. So we will take the how to consider the speed of commutator. Okay, so how to take this speed of commutator? So case 1, suppose this is the commutator, and this commutator is having the first message signal and the second message signal. So this M1T, and suppose the switch is here, and after that we are having the quantizer and then the encoder. So in encoder we will assign the 10 bits to each sample. N is equal to 10 means we are assigning the 10 bits to each sample. So tell me how many samples you will collect. Okay, now say the message signal M1T is having frequency 5 kilohertz and the M2T is having 10 kilohertz. Okay, so the message signal M1T is 5 kilohertz. We are taking the case where both the message signals are having different bandwidth. So we have already taken the case of where the message signals are having equal bandwidth, and according to that we have already calculated the bit rate. So if all the message signals are having the equal bandwidth, the bit rate is given by n into small n into fs. But how will you calculate the bit rate in this particular case? Because now how will you select the sampling frequency? Because there are two different message signals, so it is how to consider the sampling frequency. It will depend on the rotation, speed of rotation. So let's consider the speed of commutator is, the speed of this commutator is 10,000 samples per second, rotation per second. 10,000 rotations per second. Let us say the speed of commutator, this is the speed of commutator. Speed of commutator is 10,000 rotation per second. This is the speed. Okay, so this is the speed of commutator, that it is having the 10,000 rotations per second. Now, what is the sampling frequency or the Nyquist rate for the first message signal? So Nyquist rate for the first message signal is 10K. So 10K samples per second. 10K samples per second. And what is the Nyquist rate for this? So it is 20K samples per second. The Nyquist rate for the first is 10K samples per second. Okay. So what is the meaning of 10,000 rotation per second? What is the meaning of 10,000 rotation per second? What is the meaning of 10,000 rotation per second? Yes, Saurabh. Okay, so 10,000 rotation per second means this switch will rotate 10,000 times in each second. In 1 second, it will rotate 10,000 times. So when it will rotate one time, how many samples it will collect? If it rotates one time, how many samples it will collect? Yes, Manish, Nilanjana. Okay, so in one rotation it will collect 2 samples. It will collect 2 samples in one rotation. So if we are keeping the speed of this commutator as 10,000 rotation per second, it means that in 1 second it is going to rotate 10,000 times. So this switch will connect to this particular pole 10,000 times, and it will also collect the it will also connect with this pole 10,000 times. So overall at this particular point it will collect 10,000 samples of the first signal and 10,000 samples for the second signal. So this is 20K samples per rotation in 1 second, sorry, not rotation, in per second. Is it okay? So 20K samples it will collect. Yes, so all of you are saying that 20K samples it will collect if the rotation is 10,000 rotation per second. So in 1 second it will collect 20,000 samples, 10,000 samples for the first message signal, 10,000 samples for the second message signal. In this way it will collect total 20,000 samples per second. But to reconstruct the second message signal, how many samples of the second message signal should be collected? So because the Nyquist rate for the second message signal is 20,000 samples per second, it means that we have to collect 20,000 samples only for the second message signal and 10,000 samples for the first message signal. But we are able to collect only 10,000 samples for the second message signal. It means that we are not satisfying the Nyquist criteria. We are not satisfying the Nyquist criteria, hence the rotation, the speed of commutator, or you can say the bandwidth or the bit rate which is coming, that will not be valid. Here if you will calculate the bit rate is nothing but 20K samples per second. and 10 bits per sample. So we will get 200 kbps. So we will get 200 kbps. So the bandwidth we will get if we are using the Nyquist pulse. So bandwidth will be 100 kilohertz. 100 kilohertz. So although we are having the 100 kilohertz bandwidth, but it is not of use because we are not satisfying the Nyquist criteria for the second message signal. So at the receiver we will not be able to recover the second message signal. We will definitely recover our first message signal because we are collecting the 10,000 samples for the first message signal. But to reconstruct the second message signal properly, to reconstruct the M2T properly, we had to collect the 20,000 samples. But because we kept the speed of commutator as 10,000 rotation per second, it will only be able to collect the samples of 10,000 for the each signal set. For the each signal. For the each signal, it is only able to collect 10,000 samples. Is it clear to everyone? Is it clear? Now, what should we do? Tell me, what should we do? Sir, means it is only collecting one message signal samples. No, it is collecting the samples of both the message signal, but the second message signals we are not having the enough sample. For the second message signal, we are not having the enough samples to reconstruct the message signal back. Okay, because according to the sampling theorem, we know that it should always satisfy the Nyquist criteria for message signal recovery, because we are not collecting the enough samples for the second message signals, because the enough samples are 20,000, and if you are rotating it by 10,000 rotation per second, so it will only collect 10,000 samples for the first message signal and 10,000 samples for the second message signal. So remaining 10,000 are left. So that 10,000 samples if we collect, then our purpose is the purpose will be satisfied and we will be able to recover the message signal. So Nilanjana is saying that to increase the speed of rotation. So what will happen if we increase the number of rotation? Suppose if we increase the number of rotations like 20,000 rotations per second. Okay, so if this is the second case. Okay, now we are taking the second case. Now you are taking the second case. Now the second case you are saying is, so let us keep the speed of commutator as 20,000 samples, 20,000 rotation per second. So in 1 second it will collect 20,000 samples. So it will collect the 20,000 samples for the first message signal, and it will also collect the 20,000 samples for the second message signal. So overall how many samples it will collect? So tell me, how many samples it will collect? If the speed of commutator is 20,000 rotation per second, so how many samples it will collect in 1 second? 40,000 exactly. So now it is collecting a 40,000. 40,000 samples per second. Rohan? No. Arup, see, understand this point. If you are not able to recover the message signal at the receiver, then what is the use of using that bandwidth? So there is no need of calculating such bandwidth which is not able to transmit the message signal properly, because if you use 10 kilohertz signal there will be no problem, but you will be able to receive the first message signal properly because you are satisfying the Nyquist criteria only for the first message signal. You are not satisfying the Nyquist criteria for the second message signal. So at the receiver you will receive only one message signal, you will not be able to reconstruct the second message signal if you take the speed of commutator 10,000 rotation per second. I hope you got it. Now if we keep the speed of commutator as 20,000 rotation per second, we are now collecting 40,000 samples per second and 10 bits to represent the each sample. So it is 40 kilohertz and it is now 400, so it will be 200 kilohertz. So bandwidth is increasing. Bandwidth is increasing. So bandwidth is increasing, right? Now, can we make the better solution? Can we have the better solution? If you are increasing the rotation speed of commutator, you are over collecting the samples of the first message signal. Actually we wanted to calculate only 10,000 samples, but when you increase the speed of commutator and you kept it 20,000, you are actually collecting the twice of the minimum required sample. So can we have the better solution for this? So the better solution is, suppose if I connect the second message signal 2 times in the commutator. Yes, Shuyash, if I connect the second message signal 2 times in the commutator, because there are number of poles. So there are number of poles, so we are using that pole. Okay, so we are using that pole to connect the second message signal. So now we are saying that this message signal is having frequency 5 kilohertz and the Nyquist rate is 10 kilohertz, same as this one, and the second message signal is having 10 kilohertz and the Nyquist rate is 20 kilohertz, and the speed of commutator is 10,000 rotation per second. And the number of bits to encode each sample is 10 bit to represent each sample. Now tell me, will this system will be able to collect all the required samples? Sir, is there any limit of increasing the speed of commutator, or we can increase to the infinite? We cannot increase to the infinite, but there is no limit. But there, if you increase the rotation, you will find that the bandwidth is increasing. It is not happening with anything with the system. It is actually increasing your bandwidth. So you never want to have the large bandwidth of the signal. So Accordingly you have to select, because we are not having the infinite bandwidth with us. If we keep 50,000 here, if we keep 50,000, we will have the 1 lakh samples. If I keep the speed of commutator 50,000 samples per second, then I will collect 1 lakh sample, and if I will collect 1 lakh sample, the bandwidth will be increased by 10 times. So there is no use of increasing the bandwidth of the signal. Okay. Okay, now you can understand that speed of commutator is 10,000 rotation per second. It means in 1 second it will rotate 10,000 times. So it will, this switch will connect to this particular pole 10,000 times. It will also connect with this pole 10,000 times. It will also connect with this pole 10,000 times. So 10,000 and 10,000, overall we will be having 20,000. So we are now having the 20,000 samples for the second message signal, which is satisfying the Nyquist criteria. Did you get this point? This switch is now connecting with this pole 10,000 times, and also connecting with this pole 10,000 times, and also with this pole with 10,000 times. Okay. So overall now we are having, how many samples we are having at this point? How many samples we are having at this point? $30,000 samples. Okay. Yes. So 30k samples per second you will get, 10,000 each. It will give you 10,000 samples, it will give you 10,000 samples, it will give you 10,000 samples. So overall 30,000 samples you will get. So what will be the bit rate here? Now the bit rate is 30k samples per second multiplied with 10 bits per second per sample. So we will be having 300k bits per second, 300k bits per second. Now the bandwidth will be RB by 2, so it is 150 kilohertz. Okay. So in the first diagram, bandwidth was 100 kilohertz. Okay. So which one is better? So we are having these three bandwidths: first bandwidth, the second bandwidth, and the third bandwidth. So tell me, out of these three, which one is good? Manish, wait for few minutes. I am going to discuss that point also. Third one. Okay. So the third one will be best, because we will not select this 100 kilohertz bandwidth, because the second message signal was not recovered, M2T was not recovered. Why we are not selecting this bandwidth? Because M2 was not recovered, because we did not collect the enough sample for the second message signal. Here in the second case, or in the first diagram of the second case, we are able to collect the enough samples for both the message signals, but the bandwidth requirement is high. So this is the 200 kilohertz bandwidth is required to transmit the signal. Okay, now if we design it properly, if we design the commutator properly, so in this particular case we are now able to receive or able to reconstruct both the message signals, because we are collecting enough samples for both the message signals. We are satisfying the Nyquist criteria for both the message signals. We are collecting the 10 kilo samples, 10K samples for the first message signal and 20K samples for the second message signal. It means we are collecting the enough samples for both the message signals, and also the bandwidth reduced. Okay, so the bandwidth reduces compared to this particular case. So that is why we will select the bandwidth which is less. So that means what the speed of commutator, what we should select. So the speed of commutator should always be selected as minimum sampling frequency. You can note this point. The speed of commutator will always be selecting as minimum sampling frequency from all the message signal. Minimum sampling frequency from all the message signal. If message signal bandwidths are multiple of each other, okay, so the speed of commutator will be minimum sampling frequency if the message signal bandwidth are multiples of each other. Message signal bandwidth are multiples of each other. Okay, you can see that the message signal was M1T and the multiples of this integer multiple of this message signal, integer multiple. Okay, that multiple means integer multiple. That multiple means integer multiple. So this 5 and 10 are related by integer multiple. The 10 is twice of 5. So in this case the minimum sampling frequency will be the speed of commutator. In both, which one is the minimum sampling frequency? So the Nyquist rate is 10 kilohertz. So we kept the speed of commutator 10,000 and we connect the number of poles, and we consider the number of poles, more than one number of poles for the other message signal, because it is multiple of, it is twice of 5. So we connect the 2 poles. If it is 3 times of the 5, if it would have been 15 kilohertz, we could have connected 3 poles. So it depends on how much multiple is there. So if it is 3 times, so we will take 3 poles. If it is 5 times, we will take 5 poles. Is it clear to everyone? Yes. So let's consider case 3. Let's consider case 3. If it is 5 kilohertz, let us say it is 2 kilohertz and it is 5 kilohertz. Now the case 3 we are considering. Okay. So now if the message signal is 2 kilohertz and 5 kilohertz, if you take the minimum sampling frequency, because in the previous case we said that the speed of commutator will be minimum sampling frequency. So what is the minimum sampling frequency for the first message signal? The sampling frequency or the Nyquist rate is 4 kilo samples, and for the second one is 10 kilo samples. So if we take the minimum sampling frequency, that is 4 kilo rotation, 4k rotation or 4000 rotation per second. Okay, so if I take the speed of commutator 4000 rotation per second, will it work? Will it work? Tell me whether will it work or not. If it is 4000 rotation per second, how many samples you will collect? So you will collect 4000 samples for this and 4000 samples for this. So it means it is 8000 samples per second, and you are going to get 80 kilohertz. 40 kilohertz, because this is 8000 into 10, that means 80,000. So 80 kbps, and the bandwidth is 40 kilohertz. But it will not work because it is not satisfying the Nyquist criteria for the second message signal. Is it okay? Because if you take the minimum sampling frequency, the speed of commutator, if you take the minimum sampling frequency, so it is not able to satisfy the Nyquist criteria for the second signal. So the second signal we should have the 4000 samples, 10,000 samples, but it will not be able to collect all the samples. Okay, no, right? So it will not work. So if you do like, if you arrange like this, then what will happen? If you will say, suppose I am connecting it 3 times, if I am connecting this 3 times, then what will happen? Tell me now, what will happen? If I connect the second message signal 3 times, what will happen? If the speed of commutator is 4000 rotation per second, and I am connecting the second message signal 3 times, because we know that in one time it will not be able to connect the proper sample. So that is why we are now connecting it more number of times. So if I connect it 2 times, then also it will not be able to collect all the samples, because 4000, that means only 8000 samples will come. So that is why I am connecting it with the 3 number of poles. So how many samples we will get? Yes, 16,000 samples exactly, because 4000 samples from here, 4000 samples from here, 4000 samples from here, and 4000 samples from here. Okay, so for the second message signal, the required sample was 10,000, but I am collecting total 12,000 samples for the second message signal. 4 plus 4 plus 4, total 12,000 samples for the second message signals. And having more number of samples will never be a disadvantage, because if you are having more number of samples, you will be having better idea for the second message signal. So we are now having the 12,000 samples for the second message signal, but the required was 10 kilohertz, 10 kilo samples. So now overall it will be how much bandwidth will be required? So it is 160 samples per second, and multiplied with 10, so it will be 1600, and multiplied by 2, that means let me check, 16,000, 160. Okay, so 160, not, this is 16k, 10k, so it is 160 kbps, and now the RB divided by 2 is 80 kilohertz. So this bandwidth is okay. The bandwidth requires 80 kilohertz, and it will work properly. It will work properly, right? It will work properly. There will be no issue. You will be able to recover all the message signals. You will be able to recover the first message signals and also the second message signals. Okay? Is it clear to everyone? The first diagram is clear to everyone or not? Now let's discuss another case of the third one. Okay, now suppose the message signal bandwidth is 2 kilohertz, the Nyquist rate will be 4 kilohertz, the message signal bandwidth is 5 kilohertz, the Nyquist rate will be 10 kilohertz. Okay. Now tell me, what is the HCF of 4 and 10? What is the HCF of 4 and 10? What is the HCF of 4 and 10? Now, speed of commutator will be selected as HCF of sampling frequency of F1 and 2. Sampling frequency of 1 and 2. Sampling frequency of 1 and 2. Yes. So, HCF of this 4 and 10 you are selecting, which will be 2. So, this is 2K. Okay. So, the speed of commutator is now 2000 rotation per second. Okay. So, the speed of commutator we are selecting 2000 rotation per second, and along with that you are connecting the first message signal 2 times and the second message signal 5 times. Now tell me what will happen. Speed of commutator, we have kept the HCF of these two sampling frequency. HCF of these two sampling frequency. What will happen? Because I am connecting it 2 times, so it will collect the 2000 samples in each rotation. So 2000, that means 4000 samples. So 4000 samples you are collecting for the first message signal. It means that it is satisfying the Nyquist criteria, because according to the Nyquist criteria, the 4000 samples of the first message signal should be collected. So for the first message signal, anyhow we have to collect 4000 samples, and for that we selected 2 poles to connect the first message signal. So these 2 poles are connected with the first message signals, and now we are having the 4000 samples of the first message signal. And also the 2000 samples we are collecting in each rotation of the second message signal by each pole. So now 2000 and 5 times, so it means 10,000 samples, exactly 10,000 samples we are collecting. So exactly 10,000 samples we are collecting for the second message signal. It means that we are able to recover our message signal because we are satisfying the Nyquist criteria. So if you are satisfying the Nyquist criteria, so in one rotation how many samples you are collecting? So 1, 2, 3, 4, 5, 6, 7, there are 7 poles, and each will give you 2000 samples. That means you are having 14,000 samples per second, and after quantizing it and encoding you will get 14k samples, 10 bits per sample. You will be having 140 kilobits per second, and this RB by 2 is 70 kilohertz. So out of these two, which one is better? Out of these two, which one is better? Tell me, which one will be better? Second one, the last one, exactly. Even though both the systems are able to recover the message signal, the bandwidth requirement in the second case is less. So that is why we will prefer the second system. So the design of the commutator should be in such a way that the requirement of the bandwidth will be minimum, and also it should satisfy the Nyquist criteria. Is it clear to everyone how to select the commutator speed? Is it clear to everyone? Will you able to select or decide the speed of commutator now? If all the message signals are having equal bandwidth, then take the speed of commutator as minimum sampling frequency. Okay, if all the message signals are having equal bandwidth, then definitely the sampling frequency will be same for all the message signals, so that will become the speed of commutator. And if the message signals are multiple of each other, integer multiple of each other, then select the minimum sampling frequency, and how many multiples will be there, use that number of poles for that particular message signal. And the third one is, if the message signals are not multiple of each other, then calculate the sampling frequency for each message signal and then take HCF of all the sampling frequency. That will become speed of commutator. Okay, so this is all about the time division multiplexing and delta modulation. We will solve questions from this particular topic. There are 4 questions that we have to solve. So we will solve that 4 questions tomorrow. And I told you I will tell the plan for the next few days. So okay, so you might have noted it down. So I am thinking that one doubt, you take the pole in third one too. You take the number, you take pole will be there, yes. So I am thinking that tomorrow the date is 8th of October. Isn't it 8th of October, right? Yes. So 8th of October, 5 p.m. I am thinking to take the class up to 9 p.m. Okay, and will finish the band pass transmission. And 9th of October, and the 9th of October also, same time, will be completing the noise in digital communication, and also in the 10th of October, 5 p.m. to 10 p.m. noise in digital communication. Will it be okay? Will it be okay? Tell me, will it be fine? 8, 9th and 10th. So next 3 days we will be having 4-hour class. For the next 3 days, I am thinking to complete the main part of the digital communication, band pass and noise in digital communication up to 10th of October. And if it finishes in the 10th of October, then we will take one more class on Monday, that is 12th of October, and we will cover some portion of information theory. Okay, so in the last one, we will take the 12th of October. So 12th of October, we will be having, I am not telling you the time, maybe 5 to 8, yes, 5 to 8 p.m. we will be having the information theory. So in these 4 days, I am thinking to taking class, in this duration, so that it will finishes off for you. So it will be great for you, because if I take every day 2 hours, so it will take 10 days or 5, at least 1 week for this, because this is almost 5 to 10 or 9. Okay, so it is around, it will take you 4, 4, 8, and yeah, this will also be 9. So this is 12, and 12 plus 3, 15 hours class. So it is around 15 hours. If you are okay with it, then we will keep this timing, and if you are not okay with it, then we can divide it into 2 parts. Okay, so let's do one more thing. So what we do is, I am telling you about the tomorrow's timing only. So let's keep only for 1 day at least. For 8th of October, it is 5 to 9, and that we will be finishing the band pass transmission tomorrow. And tomorrow evening, I will tell the further plan, because few of you are having the crash course test on the 10th of October. So it may clash with that time. So that's why we will not keep that time for fixed now. So I will tell about the 9th of October classes, but tomorrow the class timing will be 5 to 9 for tomorrow. Okay, so tomorrow I will tell about the timing of the next classes. We can divide it into 2 parts. So if we divide it into 2 parts, so suppose I am asking you, if I divide it into 2 parts, so will you able to attend from 10 a.m. to 12 p.m.? Will you be able to attend at this timing? So tell me, will it be fine? Will it be fine? 9th of October, will it be fine? This timing will be good or not? Okay, so okay, fine. So let's keep this timing. Okay, so this is done. This is done for the 9th of October. Okay, so 9th October onwards, we will keep these 2 timings. Fine? Yes. But for tomorrow, we will be having this 4-hour class. Okay, for tomorrow, we will be having this 4-hour class. Okay, only for tomorrow, so that we will finish this band pass transmission, because it is connected topics. So if we learn in the 1 day, we will be easily able to connect all the topics. So that's why we will keep tomorrow timing 5 to 9, and from 9th of October, this is 10 a.m. to 12 p.m. and 5 p.m. to 7 p.m. That is it. Okay, good. So I am not calling it marathon because it is normal for me that taking 4-hour classes is just a normal thing. It is not like a mini marathon or marathon. I will call marathon when I will take this 12-hour class at least. Then I will be happy to say that session as a marathon session. So that's why I am not calling it as a marathon. But yes, because in the other institutes or in somewhere you will see that 60-minute marathon. What is 60-minute marathon? Every day we are attending the 120 minutes, right? 2 hours we are attending every day. So should I call it marathon every day? So that's why I will not call it marathon. Marathon means it should be very, very long and it should be around minimum 6 to 12 hours. So I will not call it. Madhav, you can ask doubt in the Telegram group. If you have not joined Telegram, you can join the Telegram group and you can post your doubts there. I will try to solve that doubts because sometimes we will be busy, so I will not be able to that. 60 minutes is a 100-meter sprint. Yes, yes, yes. Yes, Nilanjana, for the revision part, we will definitely conduct one session, marathon session for communication, when the whole syllabus will complete and when you will be able to revise it after your self-study and after practicing questions. Then we will keep one session, marathon session for the complete revision of the communication. That will be happening for the 12 hours or 8 hours or 9 hours. So that would be good idea. So that session will be session I will take in the December or January session. Yes, thank you, Saurabh. And yes, Nilanjana, I will do that. Right? Okay, so let's finish up the today's session and we will be meeting tomorrow at 5 p.m. and we will be completing the bandpass transmission tomorrow. Saurabh, you can ask anytime. There is no fixed time schedule for me and for any of us. So we cannot say the time that that time I will be available for sure. You can post your doubt. I will reply you as soon as possible. Thank you, Akansha. You can revise that video definitely. From the video, you can definitely revise all the communication. How to get the PDF of Gate Academy? There is nothing like that. Love you, Saurabh. Love you, Rick. Okay, so let's end the today's session. We'll meet tomorrow at 5 p.m. Okay, so love you all. Take care. Good night.